Today we shall look at an important aspect of our classes, and the topic is circuit geometry. Before we go into analysis of circuit geometry, the previous knowledge we need here is the knowledge of line geometry, how to apply theorems such as we have under polygons, sum of angles, in a triangle, sum of angles, in a quadrilateral, or in some other higher polygon, and also how to apply the theorems such as vertically opposite angles, alternate angles theorem, and corresponding angles theorems. Today we move on, we build on this. So for knowledge, for those who may need one help or the other on those theorems I just talked about under line and angle geometry, go back to Geometry 1 on the same YouTube channel. That's theorem says that a line that is perpendicular, a line coming from the center of circle, if it is perpendicular to a chord of that circle, then it must bisect the chord. For example, you have a line coming from the center of circle like this. The moment it is perpendicular to that chord, then it must have bisected such that this one equals to this one. So this helps us to be able to apply the idea of Pythagoras theorem. For example, they may say the distance of the center of circle to a chord is 3 centimeters. If the chord is 8 centimeters long, find the radius of the circle. All you need to do, just remember that the theorem says if you have a chord and a line is coming, the distance of this chord from the center of circle is this line. Let me call it line OM. And we are giving it to be 3. And they gave us the length of the entire chord, 8 centimeters, that is chord AB. 8 centimeters. If AB is 8 centimeters, it then means that that 8 has been divided into 4 and this 4. If you ask to find the radius of the circle, radius of circle is a line connecting the center of circle to any part of the circumference. The best way for us to want to form a triangle out here, look at it. Since OB is radius, OB is radius, OA is radius. So, and we know that the theorem already said that a line coming from center of circle, if it is perpendicular to the chord, it will bisect it. That is why we have before 4. Or if it bisects it, it must be perpendicular. That avails the opportunity of bringing out this isosceles, this right triangle where we have 3 and where we have 4. We now use Pythagoras to get the value of R, and the R there, if you solve it, we know we're going to get 5. So that is the first theorem. The second theorem, if you have a chord, look at, if I have this line and I have angle between here to be 20, if they say what sustain this angle, the gap between here and here is what sustain it. So that gap will be a straight line or an arc. So if I have this, for example, and I put this one here as 10 degrees, what sustain this 10 is the line opposite facing it. So if I have a chord like this, and I have center of the circle like this, and I have 60 here. If they're asking you what sustain this angle 60 at the center of circle, it is this chord AB. It is this chord AB. Why? Is this chord the opposite that facing this at 60? Or you simply say arc AB, this curve is arc. It's either it is arc or it is chord. Those are the two that can sustain an angle. So it is this arc AB or chord AB that sustains this 60 at the center of circle. Now, but what about if you also have something like this? And they're asking you what sustains the angle here, the angle at this circumference. What sustained it there? It is still the same arc AB. But mind you, we have 2 arcs now. There is this arc, there is this major arc, and there is this blue arc. This blue arc is minor arc, is the one that sustains this acute angle here. And you can see, if you look at the way the curve of that angle is, like, you know, both of them like this, like this. So you can see the arc like U-shaped. You can see the arc of the angle like U-shaped. So suppose is the one of this arc, that's pink arc, it would have, the angle it will sustain will be the angle here. You know, both of them will look like this. So in this case, since it is arc AB, this one that sustains 60 at the center, and the same arc sustain the angle here at angle at P, the one at P will be half of the one at center. Therefore, hence, we have the theorem that says the angle that an arc or chord sustained at the center of circle is equals to half. I mean, the one at the center is twice the one at circumference. The one, the same arc sustained on the other, on the other part of this circumference. So you will see that this arc here, already this chord has divided the circle into two segments, this place and that one. So the one of this blue is the one that sustains this angle 60 degree, and still the same arc, that blue arc that sustains this one. See all of them like you, like you. So the one at this place will be half of the one at center. So angle at center of circle is twice angle at circumference. The same way, if you look at, suppose we have something like this here. Suppose we have something like this here. If you subtract this 60 from 360, angle at a point, you get 300 here. Half of 300 is what this, the one here we sustained. The one here, if I call it Q, it will be half of 300, which is 150. So you see now, the one here, the 300 here, 300, the one here. So it's sustained by this arc, the major arc AB there. So we have talked about two theorems now. The first one is a line coming from the center of circle, if it is perpendicular to a chord, it will bisect a chord. And if it's bisect a chord, it will be perpendicular to it. And the second one is that angle sustained by a chord or an arc at the center of circle is twice the angle such a chord or arc sustained at circumference. Another one that stems directly from that theorem is, it says the angle in the same segments are equal. That is, angle sustained by the same arc or chord are equal. For example, we have this chord PR. It is PR that sustains this angle 20 degree. It is this PR called PR is the one facing the angle, is the one that sustains it. Or you say arc, this minor arc PR that sustains this 20 degree. And if we still have another angle again, for example, this one, the one at Y2, if you look at it, if you look at this angle Y, is phase, this angle Y is opposite to this PR called PR or arc PR. So that means it's like the same parents. The same parent give birth to them. And since this one is on the circumference, the other one too is on the circumference, they are equal. But suppose one is sustained, the same parent, but one is sustained at the center of circle. Then the one at center will be twice the one at circumference. But the one, this one now, this one too will be 20. That's angle in the same segment. For example, you may have diagrams such as this. If you look at this one, if this one is 80, this one too will be 80. If this one is 37, this one too will be 37. Because if you look at it, let me label A, B, C, D. If you look at what sustained this 80, is this called AB. And the same called AB that sustained this 80 as C. So if you imagine, if you remove this place, if you remove this line alone, Oh, it's removing others. Okay. If you're removing that one alone, you can see this 80 and this 80 clearly. So that's what we're trying to say there. And if you look at this one too, if you try and remove this place, if you look at this 37, this 37 for this first one, it is called CB or BC or arc BC that sustained it, that is facing it. And the same chord that also sustained 37 here. So both of them are equal. Likewise, the angle here equals to the angle here. The angle here equals to the angle here. That's what we call angle in the same segment. To quickly talk about is the theorem that says, the theorem that talks about angle in semicircle. Angle in semicircle. You know, we talk about if we have this 80 here, P, Q, the ones at the circumference will be half of the one at the center. This one will be 40. What about if we try and extend that this POQ, if we extend it to a straight line like this, and the angle has become, this is the center, that 80, we have extended it, we have stretched it to become a straight line, PQ, POQ. Instead of forming angle, acute angle here, we have stretched it out. P has come here, Q has come here, so that this one has become a straight line angle, which is 180. So the one it will now sustain at the circumference, since it's supposed to be half of the one at the center, that would be 90. Hence, we have what we call angle in semicircle. Anytime you see, anytime diameter sustained an angle, because this one has formed a diameter now, anytime the diameter sustained an angle at the circumference of circle, then such an angle is 90 degrees. So you may have something like this. You have this. So far, they mark this place at the center, then you sustain 90. Sustain 90. Is we move on to what we call the sum of opposite angle of cyclic quadrilateral. A quadrilateral is any four-sided polygon, but if all the four vertices of the polygon of that quadrilateral touch the circumference of circle, it is said to be a cyclic quadrilateral. For example, we have this one. This is cyclic quadrilateral now. But situation, if you have something like this, this is a quadrilateral, but it's not cyclic because it's not all the four vertices that touch the circumference of circle. Look at this place. The vertex here does not touch the circumference. So this is the theorem we are talking about, does not apply here. So, but if you look at this one, the theorem says that if the angle here is 100 degrees, the one facing it, the two of them must add up to 180 degrees. Therefore, the one here will be 80 degrees. If the one here is 60 degrees, the one facing it on the other hand will be 120 degrees. They must add up to, it must be supplementary. The addition must give 180 degrees. So that is what we call the sum of opposite angle of cyclic quadrilateral equals 180 degrees. So we as well move on to the aspect of tangent. Under tangent, we have the first one says a tangent is a line that touches a circle once. Touches the circle once. This is a tangent. But anytime you have a line that cuts through a circle, it's like extended chord. So all this one, we call it secants. Line like this is called secant. So we must not confuse secant for tangent. Tangent, we touch a circle. externally once. Now, the first theorem is saying that line coming from that passes through the center, and the line that will pass through the center of circle to meet the circumference, either such a line is a radius or diameter. So, for example, if you have a radius like this, any radius you have or a diameter, it forms 90 degrees with the tangent. So that means between this line and this tangent, there is a right angle. So that's what that theorem says under tangents. The second theorem under tangent that involves tangents is what we call angle in the alternate segment. You have this chord. If there is, you have this tangent. If there is a chord, let me label it. This is ABC. There is a chord D. The angle between this chord and the tangent, if it is 82 degrees, the angle between chord BD and the tangent is equals to the angle that that same chord sustained on the other part of the segment. You know, there are two segments here. If you have a circle, the chord divides circle into two segments. This is segment A, this is segment B. So you will see that it is in this smaller segment, this smaller part of circle division, that we have 82 being between the chord BD and the tangent. So if the chord now sustained another angle at the circumference of the other segment, for example, this chord BD sustained an angle here, it is chord BD that sustained this angle. This angle that chord BD sustained will be equal to the angle that between that chord BD and the tangent. So the theorem is saying that angle between a chord and the tangent equals to the angle that that same chord sustained on the other segments, or at the circumference of the other segment. So, which is this place, 82. So that means in this case, if I put an angle here, maybe I put 50 here. What sustained this angle in the first place? It is a EB. It is this chord that sustained it. Therefore, this 50 has the liberty to move down to be between that parent, that chord, and the tangent, which is this place, 50. So this 50 and this one side, they are equal, because this 50 is sustained, is the angle between the tangent, this line ABC, and chord BE. And the same chord BE that sustained this 50 here at the circumference of circle on the other segment. So they are equal. 82 equals to this one. So that is what the theorem is talking about. And lastly, on our circle geometry theorem is the one that says if you have a circle and there are two tangents that meet externally, two tangents that meet externally, two tangents to the circle that meet externally. So the thing is that if this one is X, Y, Z, the theorem is saying that two tangents that meet externally, they are of equal length, such that XY equals to XZ. If this is true, then there are a lot of things that can happen here. Number one is that I can connect XZ and see XYZ as isosceles triangles, such that the base angle will be here and here. Another thing I can do is that if I have the center of this circle, you know that the theorem, a theorem says that if a radius to this radius OY to this tangent, there is 90-degree angle between them. This other radius OZ, another 90-degree. In this case, if you look at this, and this one is R, this one is R, that will make us have this quadrilateral XY OZ as a kite because this side xy and xz is already said to be equal, and we also have oz, oy equal because that is radii. We have radius here, we have radius here. So, and the opposite angle here, this one are equal. So the line of symmetry for the kite will now be this OX. So you can use that line to divide the angle. If you have an angle here, if the angle here is given as 100, it will be 50 and 50. And you already have 90 here. If you need the angle at the center here, just apply sum of angle in the triangle. Whatever you get here is what you get here because the two triangles will now be congruent. So these are what we have under the theorem. We can now go apply this theorem to examples.